You should have chapter 1, section 3 for me, please. I'll be around in just a second to pick it up. I want to think about the scope of a quantifier, which is something we addressed last time. Want to take it a little further. So, homework. Okay, when I think about one quantifier sitting inside the scope of another quantifier, that means that the effect of the first quantifier carries through to the second one. So here is an example. For all x, for all y, the statement x plus y equals y plus x. I've seen this before. I may not have seen it written this way, but I've seen this concept before. Does the order in which you add things matter? 3 plus 2 and 2 plus 3 mean exactly the same thing. This sort of commutative rule is allowed to apply to all x and to all y at the same time. So really, I pick an x for all x. Okay, here's one. For any y I want to go with that x, I say this is going to be true or false or whatever it is. But this is read like an and for all x and for all y. If my quantifiers are the same, we can read it as an and. So in English, what does that say? Ian? Right. There are two numbers, x and y. You add them together, you get 0. Now that's not the only sentence I could make, it's still true. Here's another one. My quantifiers are different. I'm going to have to translate this differently. This isn't an and anymore. I'm not treating x and y the same here. So what does this read? How does What does this turn into, Seth?
For every x that is y, or x plus y equals 0.
Aha. Now, when you think about the logic involved in that, the method by which I would say, so pick any number you want for every x, then there is some y. That y could depend on my choice of x originally. Okay, so when I change this around, it makes it different. Now, again, this is a sentence I've probably not seen written this way, but you've seen it in arithmetic. Pick a number, any number you want, pick an x. There's some other number that when you add it to that x, you get 0, right? I don't care if you pick negative 103, whether the number you add is positive 103. But it depends on what x you picked as to what my choice of y is. This one is different still. Because of the order in which I read the quantifiers from left to right, this says something different. What does this say?
There exists an x for every y, where x plus y equals 0.
That's what it literally translates as. But the way you read it to me, it sounded very similar to the first one, right? But I guarantee you this is actually very different than the first one. There's an x, so that for every y, x plus y equals 0. Okay, wait a minute. Wait a minute. What the hell does that sentence change?
In the first one, you could pick any x and then change the y. In the second one, you have to pick one x and then all of the y's have to make it so.
Is there any number you can think of that no matter what you add to it, you're always going to get 0? Ain't no such thing, right? So it's a very good. Okay, so which one is fixed? Which one is free? Which one is allowed to be chosen in which way makes quite a bit of difference. Huh. What does that math garbage say in English? Huh?
For every x that's a real number, for every y that's a real number, if x is greater than 0 and y is equal to 0, for greater than 0, that implies that x times y is greater than 0.
Yes, that is a perfect literal translation. That's exactly what this says. For every x in the real numbers, for every y in the real numbers, if x is positive and y is positive, then xy is positive. I've never read it that way in my entire life. But I remember rules for multiplying from when I was learning to multiply in grade school. The product of two positive numbers is positive. That's what this says. But in English, the product of two positive numbers is positive. Doesn't sound like it has any quantifiers in it, does it? That's a more colloquial translation instead of a literal translation. I put it into conversational English. But it doesn't sound like there are any quantifiers in that sentence, does there? So here's a statement that in English doesn't sound quantified at all, but hiding in the context is the fact that the word any is floating around there, right? The product of any two positive numbers is positive. So there's again, we're going to have to read English carefully to look for the accurate translation of what's going on here. Questions? Let's change universes of discourse. A propositional function one with one variable, one with two variables. Oop, forgot something. For all x, c of x, or there exists y, f of x, y, and c of y. Right. The hell does this say? Ian.
So for everyone that.
Aha. For every student at Seton Hill, they either own their own computer or there is some other student at Seton Hill who is their friend and the friend owns it. Again, in English, it doesn't sound like a quantified statement. Students either own their own computers or are friends with someone who owns a computer. Now, again, the word every or all students is implied at the beginning of that sentence in English. Can add another person to the mix. What? So Z is also a member of students here. The hell does that say? Ian? But it's not just at least two people. This is a very weird circle of friends, right? There is a person so that for all of their friends, right? For any Y, for any Z, if you're friends with X and someone else is friends with X, then you're not friends with that person. This person's social circle isn't a circle, it's a star. He's at the center, all of them know and are friends with him, but none of them like each other. The vicious social. Everybody outside, everybody likes me, but everybody else, they all hate each other. I hope none of you are ever in this situation. So it's not just with some friends, all of their friends are not friends with each other. They're only friends through this one person. So really, their social group looks like that. And there are no connections between anything out here. There's someone here at Seton Hill. All of their friends are not friends with each other. What a bizarre idea. I can think of this as a looping procedure. In CS terms, I can write these as loops. For all x, there exists a y. So I'm going to go through each of the x's, right? I've got a list of x's. Maybe this list is infinite. Maybe it's just finite. But then as I go through it, you can find some y. And I don't know, maybe the same y works in multiple places. It doesn't matter. But each x, I can find one y. But the other way around, when I write that, I've got to loop through the x's until I find one x that works with every single y. For whatever property these things are doing. So that there's P of xy here, P of xy here after the comma. And I want to be able to find one so it makes the property true. Here I want to make the property true for every value of y for one particular x. Questions? Yes, sir. Sure. Let's do this one. My property is going to be x plus y equals 0, right? So if I say this, then I'm asking for every single individual x, can you find a y where when you add those two things, you get 0? We already went through, like, you pick 12, then the y that goes with it is negative 12. You pick 1.3, the y that goes with it is negative 1.3. You pick negative square root of 7, then the number that goes with it is positive square root of 7, right? No matter what x you start with, you can find some y to make it work. And the real critical thing I think of here is that my choice of y depends on my x. But if I reverse those quantifiers, if I reverse the quantifiers, you only get to pick X once. There is some X that no matter what other Y you add to it, the answer is always 0. That's a substantially different sentence, isn't it? So here, my X has to work with every single Y no matter what you pick. I don't know a number that does this. So I'm going to say this is a false statement, where the previous one was a true statement. Reversing the order of the text makes a difference. Here, X is allowed to change. And then your Y changes when you pick a new X. Here, you have to go through all the X's until you find one that works with every possible Y. Maybe numbers is the wrong thing. Are you on a team? What team are you on? Okay, so let me go through this way. I want you to go through the players. For every player, there exists a position. That player plays that position, right? You can do that, right? Every person gets a position on the team. There is a player who plays every position. Is there someone on the team who can play everything from quarterback to receiver to place kicker to holder, all of them? Not on our team. I don't know if such a person exists. But that's a big difference, isn't it? Okay. It's always important to find a context that works for you. Each player has a position. One player has all the position. Oh, you're very welcome. I will tell you that this is a math concept. I didn't pull this out of my ass. Limits. Remember limits? Vaguely, sort of. Those of you in calculus right now, this is chapter 2, section 4. I'm stealing this word for word from the calculus book. The limit as x gets closer and closer to a is equal to L. What does this mean? Visually, there's a very nice picture that goes with this. I have some x value a. I have some graph. I have a y value L. And what I'm telling you is that as you get closer and closer to this number, your y values get closer and closer to that number. How close is close enough? That's the beauty of calculus. Calculus says that this limit only works if it doesn't matter how close you want to be. You can do this for any value of closeness. I'm going to write it in symbols and you all are going to hate it. I apologize in advance. I'll make the picture match the symbols in a moment. for every epsilon positive, there is some delta, also a positive number. So that if x minus a in absolute value is between 0 and delta, then f of x minus L is less than epsilon. Now, most people upon seeing this go, what the did you just say? You better watch your mouth around me. All right, wait a minute. This says, you tell me how close you want to be to L. That's epsilon. So I go back to this picture and I say, you define a little bitty bit above or below L. So we have L plus epsilon, we have L minus epsilon. And I tell you how close you have to be for the Y values to stay inside that little horizontal belt. Now, again, as a picture, that looks really weird. But if you change the distance between those two dotted green lines going horizontally, then you could change the distance between the vertical lines. Okay. I'm going to ask, again, a question that I don't know. I don't really want the answer. I just want you to think in that fashion. If you've ever gone shooting, whether you shot a bow and arrow, a gun, if you fired at a target, even in a video game, you have to figure out where you're going to aim, right? Now, I stand here with my bow and arrow, and I don't move my hand more than about a millimeter in any direction. But I'm shooting at the target at the far end of the room. What happens? If I move my hand by a millimeter, what happens back there? I could miss. I could hit a different part of the target, right? So what this is telling me is, you tell me how big the target ring is. Your target ring is this big. You're aiming for this number. Your target ring is this big. I tell you how much wiggle room you have between a perfect shot and missing the target. And some targets are lopsided. Sometimes it's bigger on one side than it is on the other. But sometimes it's perfectly symmetric. But I'm going to tell you how much wiggle room you have in any direction. So I need to know which one's smaller, going to the left or going to the right. And then I will be able to tell you, oh, you can only go this far. You can only go this far. Now, no matter what number you pick the epsilon, I tell you a delta. You pick one for any x, for any epsilon, I give you the corresponding delta. So that's this version. For every there exists, as opposed to the other way around. I will freely admit that the text for the calc book has a much better picture than this in chapter 2, section 4. So if you still have your textbook, great. If not, you're welcome to go over to the Math Enrichment Center and look at the one they have over there. I've got mine with me because I taught calculus this morning, if you really want to see what this looks like. Questions? This is why you should either be in calculus or have taken calculus for this, because it's chock full of these examples. Let's translate the other way. Here's an English sentence. I'm in the universe of people. I would like you to translate everyone has a best friend somehow into quantifiers using this sentence, this propositional function. I should have a string of symbols in front of me. Universals, existentials, X's, Y's, other letters, whatever you want to use. How do I write this?
All of, X's,
So for all X,
for all of X, there is at least one Y.
so that
Then B of X, Y.
everyone has another person they call their best friend. Absolutely, that's the entire sentence.
I erased that, I thought it was too much, I thought I had to.
There's literally no words in there, right? For every X, for every person, you can find some other person. For every person, you can find a person and they're best friends. Now, I realize in English I said something slightly different, so let me rephrase this, let me say it again. For every person, there is a person who is the first person's best friend. What does that leave out? Or what does that include somehow? It includes the possibility that the only person I'm best friends with is me. Right? I didn't say anything about X and Y being different people, did I? The narcissist in the room, of course I'm my best friend, damn it. It makes I would hope that this person is different, right? But I didn't say that. How can I put that in here? How could I adjust this sentence? Don?
When X doesn't equal Y.
And that would have to be connected to this how? I can't just stick another thing on there. It's got to logically be connected to the first part. So, I want an and. I want them to be best friends and them to be different people. Now, nobody is their best friend is themselves. Questions? One would assume from the phrase best that this is a unique position, isn't it? Really, you have one best friend. You don't tell the other people, well, you're not my best friend. They are. You try to be polite about it, but this somehow, there should be uniqueness in it. How could I change this sentence to say that everybody has one and only one best friend? That is not themselves, Roman.
There exists an X for every Y.
So that
That X or EX, Y
Okay, but as this is written, there is a person who is, for everyone else, their best friend.
That one person is the best friend with everyone.
That's weird, isn't it? But see how simply changing the order of the quantifiers dramatically changes that? Now, I do remember a fictional universe where there was one person who was best friends with everybody, right? There's a lot, I am your best friend. The AI was always your best friend. That's not the same sentence. So this is very different. It's not a bad sentence, but it's a very different sentence. So how do I actually say it the other way around? There's a person, for every person, they have one and only one best friend. Santino, did you have your hand or was I missing?
Yeah,
We'll try anyway.
there's for every X, or no, I'm sorry, no, for one X, there's like one Y. And then like the X and Y.
And that's it?
You have X.
Okay. This sentence says, there's some person and some other person, they're best friends. But that's all it says. It says that there are people who call each other best friends. There's nothing in there that says there's only one. And it also doesn't apply to everybody, does it? This says, for some X, there is some Y that has a best friend. So you might have a best friend that I might not. You might have a best friend, you might have a best friend, you might have, but I don't. See, that's not a universally accepted statement. Everybody doesn't have one and only one best friend. This is the sentence I want to write in symbols. Selena? Aha! That was the exception of this existential quantifier. There was a way to make it unique. And now? Yes. That's my uniqueness modifier for the existential. I could do this without that exclamation point. But if I do that without the exclamation point, I need to say something far more complicated. So let me see if I can write that down. For all X, there exists Y, so that X is not Y and X and Y are best friends. Right? That says everybody has a best friend. But wait, there's more. And for anyone else, I had to bring in a third person. For anyone else, if that person is X's best friend, then really, you picked Y again. This is my best friend, Y. This is my best friend. Oh, this is Y again. That exclamation point does a lot of lifting for us, doesn't it? Questions? Please talk to me. A common occurrence in both math, solving problems, and in coding, in algorithms, and in writing code is when you run it and it doesn't do exactly what you expect it to. You've got to go back and you've got to figure out what little thing did I miss? What thing do I have to add in? What other edge case do I have to check? When I'm writing a solution to a mathematical problem, I want to do the same thing. I want to go through each step. Does that follow? Does that follow? Does that follow? Does that follow? Now, that doesn't only apply to computing problems where I'm doing calculus, or I'm doing algebra, or I'm doing trigonometry. That applies to things like geometry. Remember your high school geometry class? Here are two triangles, show they are congruent. Those two column proofs, right? Yeah. That's more what people in math do than solving problems. It's one thing to crunch a bunch of numbers. It's another thing to figure out why crunching that bunch of numbers did what it did. And we'll get there in the next couple of days for this class, because the root behind all of that is propositional logic. Here is a sentence that I stole directly from my algebra book. Every non-zero real number has a multiplicative inverse. In order for me to translate this from what is currently unintelligible geek speak to symbols that I might actually be able to understand, I need to know some things. First of all, what does the phrase multiplicative inverse mean? The internet is your friend. You tell me, what's multiplicative inverse mean? Get on Google and tell me. Ian.
It's running real numbers, numbers multiplied by
To get one. So it's the thing I multiply by to get one. Because one is the identity. When you multiply by one, you don't change stuff. So the goal is to figure out what you multiply by to get back there. Oh, okay, I'm going to make a note of that over here. Thing I multiply by to get one. So if I say, let's work in the universe of real numbers, how can I turn this into a quantified statement with propositional functions or other pieces of logic? What do I do?
First, you need to say it's a fraction.
I do?
If you have anything times the fraction, 1 over that one.
I do. So that's how I get the number. But that's not what this is saying. This just says every non-zero number has such a thing. I don't care how to find it yet. I just need to know it has one. Well, let's actually translate literally to start with. Roman?
I'm just gonna say for every x.
Let's start there. For every non-zero real number. So we're going to pick an x. For every x, if it's non-zero, then it has a multiplicative inverse. If I write it as an if then I can figure out how to translate that part, right? If it's not zero, x not zero, then. If it's not zero, then it has a multiplicative inverse. It has another number. There is some other number, so that when I multiply them together, I get one. I know the answer is it's 1 over the number I started with, but I don't care about that right at the moment. I just care, oh, there's something out there that'll multiply by. And if I started with 1/2, 1 over 1/2 is 2. That's why I don't need to know that it's a fraction in the end. It might be, it might not be. But I know now there is such a number. Interestingly enough, there are sets in math where this statement is false. It's just not about numbers anymore. If you are in computer science, at some point you will take a course called linear algebra and deal with matrices. And in the universe of matrices, there are matrices you can't multiply by and get one. Some matrices have inverses, some don't. So knowing whether or not I even have an inverse before I start looking for it is important. More questions?
I have a question about the last one, the friends one. I just didn't get to it fast enough. So for that last equation that you wrote the big thing out, yep. Does that mean that X and Z can be best friends with Y? Both of them have their best friend as Y?
This says that for everyone, there's a person other than them that they call their best friend, right? And if you picked anyone else and they were X's best friend, well, then you really just picked Y again. There is no third person. This person is my best friend. This person comes up to me and tells me they're my best friend. It better be this person. Anyone else who tells me they're my best friend better be Y. X and Y have a unique best friend. Okay. On Friday, we mentioned the idea of putting a negation in front of a quantifier. Right? What happened when we tried to move that negation from outside the quantifier to inside the quantifier? What did we say on Friday? Ian. So the opposite of everyone has a best friend is there is someone who doesn't have a best friend. When I negate compounded or nested quantifiers, I negate them one at a time. For every X, there exists a Y so that X times Y equals 1. I want the negation of this sentence. So I start moving across the quantifiers. And I say, oh, if I move the negation in, then this is going to be a there exists X instead of a universal X. I haven't moved it across that one, the second one yet. I've only moved it in the first one. When I move it across here, I reverse that quantifier as well. You won't often see not xy equals 1. More often, you'll see that. We will negate the actual math instead. What does it say? There is some number, no matter what you multiply it by, you never get 1. Up here, the original sentence said, for every X, there's some Y. When you multiply it by X, you get 1. And I wanted the opposite of that. Is this sentence true or false? What's the number? 0. The X I pick happens to be 0, and then nothing I multiply by is ever going to be 1. And that's the difference between this sentence here and this sentence here. Okay. As a math person, my goal is to make arguments, to draw conclusions using the rules of logic. As a programmer, your idea is to make good code. As a cybersecurity person, to make good defenses, to make good penetration testers. Your goal is to think carefully about how something works and what conclusions you can draw from it. Those are inferences. And in formal logic, they're going to have a set of rules for how they operate. And then we won't really do them all that formally after that. We'll do them more conversationally. But we're going to start with the formal rules on Wednesday. I will see you all then. Have a wonderful rest of your day. If you came in late and I did not get your homework or I still have homework for you, please bring it up.